Hello and welcome to the fifth part of Lesson 6. Way back in the first part of this lesson, we said that there were four mechanisms by which energy could be exchanged. By conduction, by convection, by advection and by radiation. So far we've examined the first three of these phenomena and looked at some example calculations that involve them. Now is the time to briefly examine radiative heat transfer. So let's begin by reminding ourselves where in the energy balance radiative heat transfer is involved. So here on the whiteboard I'm going to put up a slide that we saw a long time ago now, and it is all around how we formulated the energy equation and the various terms therein. And we said at that point Q is a group of terms that involve flux-based heat transfer, but we've renormalized the units of that such that it's all watts per meter cubed because the entire equation is in watts per meter cubed units. We said that that Q flux-based term contains and wraps around my conduction heat transfer, my convection heat transfer, and also my radiative heat transfer, as radiation heat transfer in some scenarios can be considered to be a flux of energy passing through a surface. And so that is going to be the start point of one of our examinations of radiative heat transfer. That, however, does mean that at that surface all the radiation is absorbed and it doesn't penetrate into the material. So actually, radiation heat transfer features in two places in the energy equation, because if we have a semi-transparent medium, as polymers may be, and all of our radiation isn't absorbed immediately at the surface, radiative heat transfer can also feature in my volumetric energy source term, because radiative energy is being absorbed by the volume of material through the depth of material. And so what we're going to do in this part of this lesson is to look at both of these instances where we can take into account radiation heat transfer as effectively another heat flux at a surface, but also where radiation heat transfer is a volumetric heat source by nature of the fact that it penetrates into the medium, because the medium is what we term semi-translucent. Alright, so let's start at the beginning. The first thing to say is that ordinarily in engineering, when we're thinking about radiation heat transfer, we tend to only take it into account when we've got high temperatures involved or large temperature differences involved. Now, when we're extruding hot polymers, actually they're quite warm, 170, 180, 190 degrees Site C, sometimes more. And so radiative cooling of polymer melts is actually significant and can be a substantial fraction of that accounted for by natural convection. So we do need a basic appreciation of this phenomenon, and we do need to understand where and when not to apply it. So let's remind ourselves about radiation heat flux. This is now where we're going to make the assumption that everything is now a surface-based effect, and all we care about is the amount of energy flux hitting a surface and it's all absorbed. Alright, so my radiative heat flux, little q sub r, which is a scalar, which is measured in watts per meter squared, can be written as follows. We have little sigma, that's my Stefan-Boltzmann constant, is 5.67 times 10 to the minus 8 watts per meter squared, Kelvin to the 4. We've got epsilon bar. Now epsilon bar is my effective emissivity based on the emissivities of the source and of the receiver of that infrared energy. And we'll talk more about epsilon bar in a minute. Script Fij is my view factor. It's how much energy emitted by one can be received by the other, and again we'll talk more about that in a minute. Then I have my temperature driving force, the difference between the fourth power of my body temperature less my far field temperature. And it's that fourth power that gives us a hint here that solving radiation heat transfer problems is inherently nonlinear. And so typically we might be looking at numerical solutions, and typically we need to be treating those numerics very, very carefully, because numerical solvers typically will struggle with that level of nonlinearity unless we've been rather careful how we formulate the problem. So let's look a little more detail about effective emissivity. Now, for perfect radiators and absorbers, the effective emissivity is 1. We've got a perfect radiator, emissivity 1, a perfect absorber, emissivity 1. The effective emissivity, which is a combination of the emitter and the absorber, is therefore equal to 1. Now, for most polymer systems, we're looking at emissivities in the span 0.9 to 1. But if the emissivity of the emitter and the emissivity of the target are different, we need to calculate what the effective emissivity actually is, and we'll do that in a second for two different examples. All right, let's now think about view factor, script Fij. Now, radiative heat transfer is all about the transfer of electromagnetic radiation from an emitter to a target. So the view factor is simply stating how much of that infrared radiation leaving the emitter is collected by the target. If my view factor is 0, none of the radiation leaving the emitter hits the target. If my view factor is fractional, some of the radiation leaving the emitter hits the target. If my view factor is equal to 1, all the radiation leaving the emitter is received by the target. So we can think about view factor in this way. It's the fraction of radiation leaving an emitter that's received by a target. We're not going to be deriving view factors for various geometries. This can get quite involved, and it is certainly a lot more than be covered in one part of one lesson. We're going to make an assumption. We're going to make an assumption that all the radiative heat transfer systems we're looking at have been designed to achieve a view factor of 1. And if we think what that means, this means that all of the target can see all of the emitter. So two geometric examples that could be, we could have two infinitely long parallel plates, one hot, one cold, and all of the cold plate can see, for want of a better word, all of the hot plate. And so all of the radiation leaving the hot plate is received by the cold plate, view factor equals 1. We can wrap that geometry around on itself to achieve something that's slightly more physically realistic and think of this cylindrically. We could have a hot cylinder inside a cold cylinder, where that cold cylinder might be a pipe. All of the hot cylinder can be seen by the cold cylinder, so that means that all of the radiative energy leaving the hot cylinder is captured by that cold cylinder. And we could think of the same thing in spherical systems as well. We could have two spheres, one inside the other, a hot one and a cold one surrounding the hot one, for example, and all the infrared radiation leaving the hot sphere is gathered by the cold sphere because the cold sphere can see all the surface area of that hot sphere. So that's what it means when a view factor is 1. Now, if you need to derive different view factors, there's extensive detail given in Chapter 13 of Inc. Repair and Dewitt and the fundamentals of heat and mass transfer. Chapter 13 is based on the 2007 edition, and that is over 1,000-page tome on the fundamentals of heat and mass transfer. So you can find pretty much anything you need in that volume. All right, let's have a little look at mixed emissivities for a minute. Let's think about that effective emissivity that we were talking about in a little more depth. Let's take the two geometric examples of view factor 1 that we've been talking about, two parallel plates and a concentric cylinder inside an annulus. And for the parallel plate example, let's say that I've got a hot plate at a far field temperature and my polymer is the cold plate. Let's say the emissivity of the far field is different to the emissivity of the polymer. The effective emissivity of the system, therefore, can be calculated as shown by that equation on the board. So that is for a planar system. If we were to wrap this around on itself, as I said earlier, we could get a hot cylinder inside which there is a cold cylinder. The view factor is 1 because all of the cold can see the hot. Let's say I've got a far field temperature T infinity and a far field emissivity epsilon infinity. The effective emissivity in this case is expressed somewhat differently because of the cylindrical coordinate system and can be calculated thus. We actually need to know the difference in area of the far field and of the cold part, which I'm calling the polymer. So that's how we can calculate the effective emissivity for two simple geometries, but two simple geometries that are quite pertinent to polymer processing. Imagine that the top geometry is a flat film being illuminated by an infrared lamp, and the bottom geometry is maybe a fibre being illuminated by a series of lamps arranged in an arcing annulus. Alright, so that's a little bit of information about the magnitude of the heat flux, and we can incorporate that into the energy equation. But when we were solving the energy equation, don't forget what we said is sit down and think about the problem. What is the dominant mode of heat transfer, and can we use that to determine, for example, whether we've got a 1D or a 2D problem? And we mentioned this and then talked about the BO number. And the BO number was the rate of heat transfer by external convection divided by the rate of heat transfer by internal conduction. And if we think about that external convection part, it was all about a heat flux leaving a surface. So it's not unreasonable to be able to say, well, let's make an analogy here, and let's formulate a BO number based on radiative heat transfer. And let's say it's the rate of external heat transfer by radiation divided by the rate of internal heat transfer by conduction. And again, we can use this radiative BO number to help us decide whether we've got a 1D or a 2D problem in exactly the same way as we did when we were dealing with convection heat transfer. And there on the whiteboard, I've put an expression for a radiative BO number. So, I mentioned at the start of this part of this lesson, we can think of radiative heat transfer in a flux-based means. It's just energy crossing a surface area, and we're assuming all that energy is absorbed at that surface, which is what we've just done. Or we can think of radiative heat transfer as a volumetric heat source, because not all of the energy is absorbed at the surface. And so let's think about that now in the context of a semi-transparent material. Now, let's imagine we have a lump of polymer. Let's assume that that lump of polymer is somewhat translucent. You can see through it. And so infrared radiation coming into the surface doesn't get entirely absorbed at the surface, but actually transmits through the thickness of the polymer. But at each point in the thickness of the polymer, the infrared transmission gets less and less and less because there's some absorption going on within the bulk of the material. And it is that absorption within the bulk of the material that is acting like my volumetric heat source. So what we can say is that now we have an additional term in our energy equation where we do have a non-zero source term in terms of watts per cubic meter. So let's define two parameters and look at their effects in a little more detail. Let's say I have a radiation intensity at the surface. It looks like a heat flux. It's got units of watts per square meter. That's the amount of electromagnetic energy hitting the surface of my polymer. That electromagnetic energy penetrates the polymer. Some of it is transmitted, some of it is absorbed. So let's deal with the bit that's absorbed. Script K bar, I'm calling my effective absorption coefficient, measured in reciprocal meters. And the further I get through my polymer, the more I will find energy is absorbed because it's a greater thickness. So, in terms of Cartesian coordinates, what we can do is we can evaluate my volumetric energy source term, S sub h, as a function of both the surface radiation intensity and the effective absorption coefficient. And it's an exponential function, as I've shown there on the board, with a dependence on the thickness of the film. So we can imagine if we're solving a radiation problem in 2 dimensions, where we've got gradients in both x and y, we can incorporate this heat transfer mode in the x direction, the thickness direction. In cylindrical coordinates, we end up with a slightly different formulation because of the coordinate system, and there on the board is an expression we can use for that. Okay, so that's how much energy is being absorbed and how to evaluate S sub h. Let's now think about values of the surface radiation intensity and values of the effective absorption coefficient. So, in terms of that first parameter, the surface radiation intensity, it's a function of the temperature of the heat source. So let's say we've got an infrared lamp, and let's say we've got a surface intensity that we can relate to that infrared lamp as follows. And we can see that it is dependent on the temperature of that heat source. And you can look in the literature and find out specific values for different kinds of heat source. What about the effective absorption coefficient? Well, we might expect that to have a material dependency, and indeed it does. And literature on this tends to be a little more sparse, but on the board I've put an example of that effective absorption coefficient for polyethylene terephthalate, PET, or polyester as it might be generically known. And we can see again it has a dependence on the temperature of the source. Moreover, it also has a temperature range over which it's valid, because it's effectively a correlation and it's going to have a valid range. So what these allows us to do is to work out the intensity of the radiation at the surface, to work out what the effective absorption coefficient based on the heat source, and then work out what the volumetric energy source term would be in the energy equation as a function of position through the material. All right, okay, let's summarize a few key points. So we've had a very quick whip through the fundamentals of radiation heat transfer. Fundamentally, it does matter in polymer processing, and there are situations where we do have to take it into account. It's typically significant when hot materials are cooling in free air, or when we're dealing with radiative heat transfer, for example, for a secondary heating step to relax stresses in a spun or extruded material. Now, we've had an incredibly fast walk through these basics. If you need more information about radiation heat transfer, do have a look at, for example, Increper and DeWitt, Fundamentals Heat and Mass Transfer, and it goes into a lot more depth. The final part of this lesson, however, is going to look at how we might solve numerically the energy equation when we incorporate radiation. So I'm hoping that that example will cover most of the practical application that you'll need to put this material to.